Bismillahirrahmanirrahim. The topic of our today's lecture is kinematics of fluid flow. Up till now, we have studied the effect of force on the liquid at rest. Now we will study the motion on liquids without any reference to the force causing motion. It means that this lecture deals with the study of velocity and acceleration of the liquid particles without taking any consideration of any force or energy. Before going into the detail, first I would explain some flow types. The flow can be categorized into different ways, like according to compressibility, according to uh, shape of the object, or whether it is flowing under gravity or pressurized, or it can be classified according to different numbers like Froude number, Reynold number, Mach number, Euler number, etc. So these numbers will be discussed in detail in future lectures. And after explaining these flow types, we will discuss the continuity equation and we will solve related numerical. And then in the future lecture, we will discuss Bernoulli's theorem and its application in real life. And we will discuss, and then we will solve some numericals related to Bernoulli equation. First, we will discuss the equation on ideal fluid, and then we will discuss the equation on a real fluid. So let's start our today's lecture with different types of flow. So first type is according to compressibility, like flow is either compressible or it is incompressible. What is the meaning of compressible flow? A flow in which the volume of fluid and its density changes during the flow is compressible flow, and if the volume and especially the density remain constant during the flow, then it is incompressible flow. So the gases are an example of compressible flow, while the liquids are generally considered to have incompressible flows as their density do not change during the flow. The next flow type is according to steady and unsteady flow. So what is a steady flow? A flow in which fluid characteristics like velocity, pressure, density and discharge, etc. at any point in a stream remains constant with respect to time, but the conditions may be different at different points is called steady flow. And if these flow conditions like velocity, pressure, density, discharge, etc. at any point in a stream changes with respect to time, then it is called unsteady flow. It can be further explained like by drawing a cross section. See if this is a cross section of a stream at different points. I label these cross sections as 1, 2 and 3. If we measure these characteristics like velocity or discharge etc. at section 1 after different intervals like after 10 seconds, 20 seconds, 30 seconds or after a minute, then if these characteristics do not change, and then it is a steady flow. But these conditions at point 1 may be different from point 2 or from point 3, but at a particular point these should not change with respect to time, then this is a steady flow, otherwise this is an unsteady flow. So example of a steady flow is a flow through a prismatic or non-prismatic conduit at a constant flow rate. And what is prismatic conduit? A conduit which has constant size or shape is known as a prismatic conduit. So steady flow can be in a prismatic, can exist in a prismatic channel, or it can also exist in non-prismatic channel, provided the condition described here is fulfilled. And what is the example of unsteady flow? An unsteady flow example is the flow in a pipe like whose valve is being opened or closed gradually. So if if this is a pipe and there is a valve at the start, which you open or close gradually, then the flow conditions like discharge or velocity etc. will change at this point. For example, at point 1, if the valve is being closed gradually, then the velocity will change with respect to time at this particular point, then this is an example of unsteady flow. Now let's discuss another flow type, which is uniform and non-uniform flow. So what is a uniform flow? If the flow velocity at a given instant of time does not change within a given length of pipe or channel, then the flow is called uniform flow. And if the flow velocity at a given instant of time changes within a given length of pipe or channel, then the flow is called a non-uniform flow. So it can be also explained with the help of drawing a cross section. For example, this is a cross section of a pipe or a channel. So if these are different points in a cross section and we measure the velocity at all these points at a particular time, for example after 10 seconds, the velocity remains same at all these points, then it is a uniform flow. Then we measure the reading after, let's say, 30 seconds, and the flow velocity at same at all these points, point 1, 2 and 3, then it is a uniform flow. The reading may be different at these two times. So it is irrespective of the time, it depends upon the distance. So within a given length at a particular instant, if the velocity remains constant, then it is a uniform flow, otherwise it is a non-uniform flow. So some examples of a uniform, an example of a uniform flow is flow through a straight prismatic conduit. It means that flow through a straight pipe of constant diameter is an example of uniform flow. That is, if it is a straight pipe and it is of a constant diameter, then at every point the then at every point the flow velocity will remain the same. Because if discharge is constant from the source and the area is constant, then the velocity will not change at any of these points. So this is an example of uniform flow. And the example of non-uniform flow is flow through a non-prismatic conduit, or flow around a uniform diameter pipe, bend, etc. is an example of non-uniform flow. The flow types which we have recently discussed can exist in different combinations. Like flow can be steady uniform flow, it can be steady non-uniform flow, unsteady uniform flow, or unsteady non-uniform flow. So what is the meaning of steady uniform flow? So steady uniform flow means if the conditions do not change with position in stream or with time. Which conditions means the flow characteristics like velocity, discharge, etc. If these conditions do not change with position and with time, then it is a steady uniform flow. If the conditions change from point to point in the stream but do not change with time, then it is steady non-uniform flow. If the conditions at a given instant in time, the conditions at every point are same but change with time, then it is unsteady uniform flow. And if every condition of the flow may change from point to point and with time at every point, then this is an unsteady non-uniform flow. So flow can exist in combination. An important thing which is to be discussed is that unsteady flow is a transient phenomena. That is, unsteady flow either becomes steady after a certain time interval or it becomes zero. For example, here is an example of a stream. This is the channel bed, and this A point denotes the surface of the stream that has just been admitted to the bed of the canal by sudden opening of a gate. For example, if there is a gate in the stream and we have allowed the discharge into this canal, then air presents the surface of that stream which is just admitted to the bed of the canal. After a certain time, water surface will be at B and then later at C, and then it will reach at equilibrium at point D. So at D, the unsteady flow has become steady. So if the opposite case happens, that is, if you close the gate, then it will move from point D to point A, and then it becomes 0. So unsteady flow is a temporary phenomena which may in time becomes either steady or zero flow. Another flow characterization is according to viscosity. So what are viscous flows? The viscous flows may be classified into following two types depending upon the factor whether the viscosity is dominating or not. This is laminar flow and turbulent flow. So most of you may be familiar with the Reynold number, or maybe may have heard the name of the scientist Osborne Reynold. He is a scientist who has demonstrated an experiment to distinguish these two types of flow. Let's have a look of his experiment. Osborne Reynold demonstrated in 1883 that there are two distinctly different types of fluid flow. How he has done this? He has injected a fine thread-like stream of colored liquid having same density as water at the entrance to a large glass tube through which water flowing from a tank. A valve at the discharge end permitted him to vary the flow. When the velocity in the tube was small, he saw this colored liquid as straight line throughout the length of the tube, showing that the particles of water moved in a parallel straight lines. As he gradually increased the velocity of water by opening the valve further at a certain velocity, the flow changed. The line first became wavy, and then at a short distance from the entrance, it broke into numerous vortices, beyond which the color became uniformly diffused so that no streamlines could be distinguished. Later observations have shown that in this latter type of flow, the velocities are continuously subject to irregular fluctuations. उसके पास एक टैंक था, ठीक है. उसमें से उसने क्या किया कि एक सिंपल उसने डाई इंजेक्ट किया और वॉल्व ये लगा था, इससे उसने फ्लो को रेगुलेट किया, यानी कि वेलोसिटी जो थी वो कम या ज़्यादा की. जो पाइप है उसका डायामीटर कांस्टेंट था, जो लिक्विड है उसकी विस्कोसिटी भी कांस्टेंट थी. तो ओनली चीज जो वेरी कर रही थी वो वेलोसिटी थी. जब उसने एक्सपेरिमेंट परफॉर्म किया, डिफरेंट यहाँ से वेलोसिटी को वेरी करा के तो नोट किया कि जब वेलोसिटी कम थी तो जो भी पार्टिकल्स थे वो एक स्ट्रेट लाइन में ट्रेवल कर रहे थे. ये कैसे उसने डिटेक्ट किया? जो डाई इंजेक्ट किया था वो ट्रेस कर रहा था पार्टिकल्स के पाथ को. एंड जैसे जैसे इस वॉल्व को ज़्यादा ओपन करता गया, यानी कि वेलोसिटी इंक्रीज होती गई, वैसे वैसे नोट किया कि जो पार्टिकल्स थे उनकी मोशन इरेगुलर हो गई. इसके अकॉर्डिंगली उसने डिफ्रेंशिएट किया फ्लो को एज लैमिनार एंड टर्बुलेंट, और एक नंबर उसने डिस्कवर किया जिसको रेनॉल्ड नंबर कहते हैं, जिसका फॉर्मूला है R = dV/ν. Here dia of pipe is constant. The kinematic viscosity of liquid flowing in the pipe is constant. The only thing which is variable is velocity of the fluid. So as long as the velocity is small, the Reynold number is small and the flow is laminar, and when the velocity increases, the Reynold number increases and the flow is termed as turbulent flow. So the limiting value of Reynold number in case of pipe flow is 2000, which is known as critical Reynold number. From 2000 to 4000 the flow is transitional, and for more than 4000 the flow becomes turbulent. These values are for pipe flow. So what is a laminar flow? The first type of flow is known as laminar flow, streamline or viscous flow. Now, the laminar flow can be defined as if the liquid particles appear to move in definite smooth paths and flow appears to be like this, then this is laminar flow. Here you can see the stream of water coming from this tap. All the particles are streamlined. So this is laminar flow. And what is turbulent flow? The second type of flow is known as turbulent flow, where the liquid particles move in irregular path like this as shown in the figure. Or in real life example, if you put a cup beneath a jet of water coming from a tap, the water moves in irregular direction after it gets strike with the cup. This is turbulent flow. So this flow is laminar flow, flowing in a straight path. Then transition occurs, and then when the velocities further increase, the flow becomes completely irregular, known as turbulent flow. So the laminar flow example is flow through a capillary tube, or flow of blood in veins and arteries, or groundwater flow. All these are the laminar flow examples. And turbulent flow examples: high velocity flow in a conduit of large size. Nearly all fluid flow problems encountered in engineering practice have a turbulent characteristics. So these laminar and turbulent flow will be discussed in detail in advanced fluid mechanics. So there are some more terms which are to be defined, like path lines, streamlines, and streak lines. So what is a path line? A path line is a trace made by a single particle over a period of time, or the path followed by a fluid particle in motion is called path line. Thus the path line shows the direction of particle for a certain period of time or between two given sections. The next term is streamline. Streamline show the mean direction of a number of particles at same instant of time. The imaginary line drawn in the fluid in such a way that tangent to any point gives the direction of motion at the point is called streamlines. If the flow is steady flow, then path lines and streamlines are identical. So what is a path line? Path line is trace made by a single particle, and streamline show the mean direction of number of particles. The last term is streak line. What is streak line? In experimental fluid mechanics, a dye or other tracer is frequently injected in the flow to trace the motion of fluid particles. If the flow is laminar, a ribbon of color results. This is called streak line or filament line. The instantaneous picture of motion of all fluid particles in flow which have passed through a given point are called streak lines. So its examples are the line formed by smoke particles ejected from a nozzle, or the line of color in a flow into which a dye is continuously introduced through a small tube. All dyed fluid particles have passed the tubes, and these are the examples of streak lines. So a streak line is a physical line. Like stream line, which we have discussed, is an imaginary line, and streak line is a physical line of particles that have passed through some position in the flow field. So in case of steady flow, streamlines, streak lines, and path lines coincide. Or we can say that in case of steady flow, there is no geometrical distinction between streamlines, path lines, and streak lines, and they are coincident if they originate at the same point. While for an unsteady flow, for example, a person giving out whiff of smoke from a cigarette, the path, streak, and streamlines are all different. So these were the few important definitions, and now let's move towards the equation of continuity. And before moving towards the equation of continuity, first we have to describe rate of discharge. So what is rate of discharge, or simply discharge? The quantity of liquid flowing per second through a section of pipe or channel is known as rate of discharge, or simply discharge. In fluid mechanics, we denote discharge by capital Q. Now consider a liquid flowing through a pipe. Let small a is cross-sectional area of the pipe and v is average velocity of liquid. Then discharge Q can be defined mathematically as equals to product of area into velocity. The units of discharge are Qmix or Q6. If we are working in SI system, then it is cubic meter per second, and if we are working in FPS system, then it is cubic feet per second. There are some other units of discharge which are also common, like gallons per day, gallons per minute, or liters per day, liters per minute, etc. Now we will discuss equation of continuity. What is equation of continuity? If an incompressible liquid is continuously flowing through a pipe or a channel whose cross-sectional area may or may not be constant, the quantity of liquid passing per second is same at all sections. This is known as equation of continuity of liquid flow. इसको हम elaborate करेंगे by considering a tapering pipe through which some liquid is flowing. टेपरिंग पाइप मीन्स ऐसा पाइप जिसका क्रॉस सेक्शन चेंज हो रहा है. आप जैसे देख रहे हैं ये इस पे 3 सेक्शंस हमने काटे हुए हैं. ये पाइप है. सेक्शन 1 में डायमीटर ज़्यादा है, देन स्लोली पाइप का डाया कम हो रहा है. तो दिस इज़ अ टेपरिंग पाइप जिसमें डायमीटर चेंज हो रहा. जो डिफरेंट पॉइंट्स हैं 1, 2 एंड 3, इनमें जो डायाज हैं या जो एरियाज हैं उनको हम A1, A2, A3 से डिनोट कर देंगे, और इसी तरीके से जो इन पॉइंट्स पे वेलोसिटी होगी उसको V1, V2 और V3 से डिनोट कर देंगे. Let A1 is cross-sectional area of pipe at section 1, V1 is velocity of liquid at section 2. Similarly, A2, V2 and A3, V3 are corresponding values at section 2 and section 3. We know the total quantity of liquid passing through section 1 Q1 is equals to A1 V1. Similarly, total quantity of liquid passing through section 2 is Q2 equals A2 V2, and total quantity of liquid passing through section 3 is Q3 equals A3 V3. From law of conservation of matter, we know that total quantity of liquid passing through sections 1, 2 and 3 is same. Therefore, Q1 equals Q2 equals Q3 or A1 V1 equals A2 V2 equals A3 V3. So discharge जो है, जो पीछे से आ रहा है इस पाइप के अंदर, वो चेंज नहीं हो रहा है. वो तीनों पॉइंट्स पे सेम होगा. और अगर आप इसमें और भी फर्दर पॉइंट्स ले लेते हैं तो सब पॉइंट्स के ऊपर डिस्चार्ज सेम रहेगा. कि अगर आपका एरिया चेंज हो रहा है तो अकॉर्डिंगली आपकी वेलोसिटी भी चेंज होगी, लेकिन दोनों का जो प्रोडक्ट होगा जो मिलकर डिस्चार्ज बना रहा है वो सेम होगा हर पॉइंट के ऊपर. सो दिस इज नोन एज इक्वेशन ऑफ कंटिन्यूटी. Q1 equals Q2 equals Q3 and so on. So now we will solve a simple numerical related to this equation of continuity. So here is the statement of the question. The diameter of pipe at section 11 and 22 are 200 mm and 300 mm respectively. If the velocity of water flowing through the pipe at section 11 is 4 meter per second, find discharge through the pipe and velocity of water at section 22. आपको एक पाइप गिवन है जिसका आपको डाया बता दिया गया है दोनों सेक्शंस के ऊपर. यहाँ पे मेंशन है, दो आपने सेक्शंस काट लिए हैं, एक 1-1 है, एक 2-2 है. वहाँ पे डाया 200 एंड 300 मिलीमीटर है, यानी पहले स्मॉल ओपनिंग थी, देन डाया पाइप का एनलार्ज हो रहा है और चेंज हो रहा है 200 से 300 मिलीमीटर के ऊपर. और साथ में आपको सेक्शन 1-1 के ऊपर वेलोसिटी गिवन है, दैट इज 4 मीटर पर सेकेंड. आपने टोटल डिस्चार्ज फाइंड करना है जो इस पाइप में से ट्रेवल कर रहा है, और वेलोसिटी फाइंड करनी है सेक्शन 2-2 के ऊपर. So this is the figure. At section 1-1, dia is 200 millimeter. At section 2-2, dia is 300 millimeter. You have to calculate the discharge and you have to find out the velocity at this section. So this is a pretty simple question. We can solve it very easily by applying the equation of continuity. First of all, we have to calculate the area of the pipe at these two different sections. So at section 1, area is equals to pi by 4 d1 square, and at section 2, area will be calculated by applying the formula pi by 4 d2 square. So upon putting the respective values of d1 and d2, we get areas at section 1 as 0.0314 meter square, and at section 2 area is 0.0707 meter square. Now first we will calculate the discharge, as we know the relation that Q equals A1 B1. So upon entering the value of A1 and B1, which is 4 meter, which is given in the question, and upon multiplying, we get the discharge as 0.1256 cubics. As units of area are meter square and units of velocity is meter per second, so the units of discharge are cubic meter per second. Now we have to find the velocity of water at section 2. So upon using the equation of continuity as Q1 equals to Q2, the discharge will remain same at these 2 points, and A1 V1 equals A2 V2. So upon entering all the values, only V2 is unknown, all the other values are known. So we get the velocity at section 2 as 1.77 meter per second. So this is our today's lecture, and next lecture we will discuss Bernoulli's theorem, related numericals, and application to real world problem.